So we've seen that Lipschitz functions can be defined between metric spaces. So in particular, they can be defined on subsets of the Euclidean space. In this video, we'll show how we can actually extend some Lipschitz functions to all of Euclidean space. And so we can think of these functions that are initially defined on subsets as actually being restrictions of globally defined functions. So why is this important? So why do we need Lipschitz extensions? Well, one reason is that many results for Lipschitz functions are stated for functions that are globally defined. So, for example, let's recall that a function f has a derivative at a point x if the limit as r goes to 0 of the supremum over y inside this ball of the difference between y and its sort of first order Taylor approximation, or this linear approximation, divided by r goes to 0. So the function f is well approximated by an affine map on small scales at x. Then Rademacher's theorem says that for a Lipschitz function defined on all of Euclidean space going into another Euclidean space, it's differentiable Lebesgue almost everywhere. Now, you notice that if we define f on a subset instead, then we can still make sense of the notion of a derivative. In this definition, we just have to take the intersection of this ball with the set E, where the function is defined. Okay? So then the natural question is, does Rademacher's theorem hold for functions defined on subsets of Euclidean space? So the answer is yes, because we have certain theorems that say that given a Lipschitz function on a subset, we can actually extend it to all of Euclidean space, where we can apply Rademacher's theorem to that globally defined function. So what do I mean by an extension? So given a function f defined on a subset E of a metric space into another metric space, we say that an extension of f to x is another function big F defined on the whole metric space going into the same range space, so that when restricted to the set E, it agrees with f. Okay, so an important question is, under what circumstances can we extend a Lipschitz function or Bi-Lipschitz function to another Lipschitz or Bi-Lipschitz function, respectively? The first extension theorem we'll discuss is a simple one called the McShane-Whitney extension theorem. So suppose we have a metric space X and the subset A, the metric space, and suppose that we have an L-Lipschitz function f defined on A going into the reals. Then we can find another L-Lipschitz function that extends the function f to all of the metric space X. So the proof of this extension theorem is not too bad, so let's go through it. We can actually write down the extension explicitly. So the extension is equal to the infimum over all y in the set A of L times the distance between x and y plus f of y. Okay, so there are a couple things that we have to check. We have to first check that this equals f on the original set A, and then we have to check that it's also L-Lipschitz. So let's prove the first one. So claim f is equal to f on A. So let x be an element of the set A. So notice by the definition of this infimum is at most the value that we get that by just plugging in y equals x, and in that case we just get f of x. So immediately we see that big F of x is at most little f of x. So now we just need to prove the opposite inequality. So let epsilon be bigger than 0, and let's pick y in A so that L of x minus y plus f of y is very close to the infimum. So let's say it's less than f of x plus epsilon. So this implies if we subtract f of x from both sides, we get L of x minus y plus f of y minus f of x is at most big F of x minus little f of x plus epsilon. Now, recall that now y and x are both in the set A. And because f is a Lipschitz, that implies that this difference right here is greater than or equal to minus L of x minus y. And thus, that means that this sum of Lxy plus Fy minus f of x is non-negative. Okay, so now we have that this right here is non-negative. So this implies that f of x is at most big F of x plus epsilon for all epsilon bigger than 0. And now we just let epsilon go to 0. And that proves the claim that f of x is equal to f of x. So now what remains to show is that this function is still Lipschitz. Okay, so let x and y be any pair of points in the whole metric space X. And then we're going to pick Z in our set A such that if we look again at the difference between x, y minus z plus f of z, that this is less than f of y plus epsilon. Okay, so now let's look at this difference. So if we look at f of x minus f of y, okay, so notice that f is defined to be an infimum over all points in A. So in particular, it's less than this quantity if we just let y equal z. So this is going to be at most L of x minus z plus little f of z. And then here we use the reverse of this inequality. So because this is at most f of y plus epsilon, that means that minus f of y is less than L times y minus z plus f of y, minus f of z plus f of z minus epsilon. Okay, so notice that this f of z and this f of z are going to cancel. And by the reverse triangle inequality, we can combine x minus z minus y minus z and bound that above by, so this will just be at most L of x minus y. And then we have minus minus epsilon plus epsilon. And then now we let epsilon go to 0. And then we get that f of x minus f of y is at most L of x minus y. And then if we reverse the roles of x and y, we get that the negative f of y minus f of x is at most this L times x minus y as well. And that implies the absolute value is at most this distance. And that improves Lipschitzness. Now, if instead we have an Lipschitz function from a subset of a metric space into an n-dimensional Euclidean space, what we can do is apply the first part of this extension theorem to each coordinate and then combine the functions into a square root n at times L Lipschitz extension. However, if our function is defined on a subset of a Hilbert space and it's mapping into another Hilbert space, then Kersbron's extension theorem says that we can extend this function to a Lipschitz function on the entire Hilbert space and without any change in the Lipschitz constant. Now, Bi-Lipschitz extensions are much harder to guarantee, even in very simple scenarios. So for example, let's consider a map that takes a subset from the real line to itself. So it'll take the points 0, 1, and 2, and it'll take them to the same 3 points. It's going to take 0 to 0, but then it's going to take 1 to the point 2, and it's going to take 2 to the point 1. So this Bi-Lipschitz map from 3 points to 3 points in the real line cannot be extended even to a continuous injective function of the real line into itself. However, a very simple extension lemma of McManus says that we can always extend a Bi-Lipschitz map from a subset of Rn going into Rn. We can extend this to a Bi-Lipschitz map from R2n to itself. So that is to say, we can extend any Bi-Lipschitz map if we're willing to add on extra dimensions. Where by extend in this case, we mean that, so there is a function f from Rn cross Rn to R2n. So Rn cross Rn is the same as R2n. So that if we plug in f of x0, we get f of x, comma, 0. And the proof of this is not too difficult. I'll just show a little bit of details and you can verify the rest on your own. So first of all, observe that since the function f is Bi-Lipschitz, it's Lipschitz, which means that it has a Lipschitz extension, which we'll call f1. Similarly, the inverse of this map, defined on the image of k under f, has a Lipschitz extension as well, and we'll denote that function f sub 2. Then we define two new functions. So f1 of xy is y plus f1 of x comma x, and then we define the function f2 of xy is equal to x comma y plus f2 of x. Then it's not too hard to verify that if we look at the composition F2 inverse with F1, that if we plug in x comma 0, then following this chain of equalities, you can see that you get f of x comma 0 outside.